For our final speaker for the morning, we've got Côté from Mozilla, who will be giving us a nice introduction to network programming for automation developers. I'll let him introduce himself.
Hey, how y'all doing? My name is Côté. I'm part of Mozilla, specifically the automation and tools team. We do automated testing frameworks and various other tools and what have you to basically make everybody else's lives at Mozilla easier. Just a couple of introductory notes. So this is a novice talk, but not necessarily just for novices. The thing about automation developers is we tend to be generalists, so we know a whole lot about a bunch of topics, but not necessarily in-depth knowledge on any particular topic. And so something that's kind of come up in my work a lot recently is socket programming, network programming, and realizing that the developers that we have are all awesome and everything, but they may not necessarily be have a lot of experience in socket programming. So you don't have to necessarily be an intro novice to Python to appreciate this talk. Similarly, if you know a lot about networking, some of this is probably going to be pretty basic. Some of it might be more interesting. And I'm not going to go really in-depth on exactly how socket programming in Python works. There's plenty of resources that do a better job than I would. I'm more just kind of giving tips and advice and things in the context of programming for automation. I'll get more into exactly what that means in a little bit. And I'm talking more about socket programming, not necessarily some of the frameworks. There's 1,000 frameworks for network programming. I'm going to be talking a little bit more at the lower level, like of the actual socket objects and things, just because I found that a lot of these frameworks make certain tasks really, really easy and make other tasks more difficult, and so we end up often just kind of going down to the lower level for what we need to do. And if you understand the lower level of sockets, you understand the higher level kind of by default. And I'm going to be focusing a lot on more client development than server development. That's primarily because when we're talking about automation of remote devices, the remote devices tend to be flaky and they tend to be more resource constrained. So we may not have Python on the actual devices. Often we have to write clients in C++ or some other language that's supported directly by the device. So the Python side of things tends to come in when we're working on our clients. Especially since the client is the kind of point of contact with the test framework, it's where you have to catch a lot of the errors and everything. You can't really rely on the server on the device, like a phone or whatever, to stand up. They tend to fall over a lot more than your client machines do. All right, so let's get into it. So why am I giving this talk? I think it's probably fairly obvious, but just in case it's not. Automation, controlling things remotely, we're dealing more and more with mobile computing. Specifically at Mozilla, we've got Fennec, the Firefox for Android that we're continually working on and testing, and we've got the upcoming Firefox OS phones that need all kinds of automation because more testing equals more better, and the more tests you have, the more you have to automate them. And as I mentioned, this is not, you don't have to necessarily be, whoa, nice spelling error, don't pay attention to that. You don't have to be necessarily new to Python, but you might not have done a lot of network programming. And obviously Python tends to be the language of choice for automation projects. It just makes things, easier and more fault tolerant, and you can get stuff off the ground quickly, and that extends all the way down to socket programming. I got started in network programming in C++, and when I discovered Python, you can just get like a client or a server off the ground in almost no time at all. It's just super easy, but maybe it's a little too easy. Not really, but what I mean by that is it's really easy with Python to just start jumping in and coding up a storm, and you need, when you're doing automation, and specifically in the networking area, you need a lot of forethought before you really start coding up something. You can do a lot of experiments and everything, but experiments and prototypes have a tendency of turning into products. So to stop and think, I guess other people have had that experience. So to stop and think for a while before you really start getting down to business will pay off a lot in the end. This whole talk is basically compiled from my experiences working on our automation we have a Python client called the device manager that interfaces with our phones. The phones run a Java Android application we call the SUT client, and then the new Firefox OS ones have a cross-platform C++ agent. So I just noticed a lot of things going on in our code that didn't really make a lot of sense, and while trying to restore some sanity and figure out just why certain things were behaving, I just kind of came up with this talk in the course of doing my job, basically. So I'm going to break this up into three. It's going to be a lot, so I might have to go a little fast, but break it into three categories. Just some basic socket tips. Again, I'm not going to get into how you open sockets and everything. The socket documentation is good for that, but more just some gotchas and things you may not know about. Error handling and recovery. This is an extremely important topic in automation. There's sort of an overarching theme, I think, through my whole talk that you want to expose errors as soon as they happen and in as much detail as possible. Don't hide these things because then you have to spend hours of sifting through logs and replaying scenarios to try to figure out what went wrong, when if you just expose the error up front, you'd be able to figure out and fix it quicker. And then a couple of notes on designing effective protocols for automation specifically. So there's a lot to know about sockets, obviously. I'm going to touch mostly just on two topics here. The first one being timeouts, and the second one being about connections. These seem kind of obvious, but when it comes down to the details, they're not necessarily that obvious. Timeouts specifically. Blocking sockets, I don't know how much you guys know about sockets in particular, but the default way that you normally use a socket is in blocking mode. You want to receive some data, you just call out to a receive function and you sit back and wait until your data comes in and then you process it. It's really simple. It's recommended for when you're doing really simple non-parallel architectures such as in simple clients. Well, the thing is, in automation, you don't normally want to wait forever for something to happen. That'll tie up your whole testing framework. So you basically want to wait a certain amount of time. This is all very context dependent, and there's no kind of magic rule for that. But if you're on a local network and you've got a device that's relatively responsive, if you're waiting more than 5-10 seconds for a response to a simple operation, there's probably something that's gone wrong. You might want to set a more liberal timeout than that, but having the timeout happen at the socket level, saying, a minute or 30 seconds or whatever went by and I didn't get any data, that's a lot more informative an error than just the whole test. Your testing framework times out after 5 minutes or whatever, and then you got to sift through the logs and, was the test just taking too long, or where was the stalls happening? If you just bubble up an error that says, this particular socket call took way too long, then you know that you've lost a connection or something like that. There's different methods for doing timeouts. Common approaches are with the select call, which just waits on file descriptors, or the socket object itself has a set timeout, which puts it into non-blocking mode. We'll get into that, but pick a method anyway. They're both kind of equivalent, and make sure you implement it correctly and make sure you test it that your timeouts are actually going to work so you're not sitting there waiting forever on something. This surprised me that actually it's not that obvious to a lot of people how you even tell if a connection closed. I saw some kind of crazy things in code before where people are using, timeouts to say, oh, I haven't gotten anything in this amount of time, so I guess the connection's closed. But I mean, anything could be happening if you haven't gotten any data in a while, or, they'll just kind of read a bunch and assume that that's all they're getting, and then they'll move on. And really, it's quite simple. If your receive function returns none, your connection has been closed, more or less normally. A hang up on the other end or whatever. So just look for that and then deal with the fact that you've got a closed connection. If it's expected or unexpected, I'll get into the error part of that afterwards. Abnormal disconnections are raised as exceptions, like socket.error. And if you're in a non-blocking mode, like if you're using set timeout and there's no data available within a certain time, you'll get a different kind of exception. I think it's a socket.timeout exception. It's basically the C equivalent of an E again, which means there was no data available right now, but there might be more data in the future. So make sure you catch those exceptions and process them appropriately. Just because if you get no data back, it doesn't mean that there was no data available. It means your connection's been closed. And actually, the sample code in the socket documentation on Python at the bottom of the main page about sockets actually describes this, but they don't really call it out. It's just, I think the people who wrote this were probably, have been doing network programming for a really long time and just thought it was obvious, but I have found that it's not obvious to people. 10 minutes already. Oh, okay, all right. Second section, errors. Well, I hate them, but you're going to have to deal with them if you're in automation. We have flaky devices, these development boards that are always erroring out, and errors just happen. And it's really tempting to say, oh, I'll write the basic logic of this and then kind of wrap all the errors and handle them later. That's just a recipe for total confusion because there's a lot of different classes of errors that you got to deal with, and you got to know what errors require what kind of responses. Just on actual mechanics of it, if you've come from C and you've moved into Python, you probably would instinctively want to use things like return codes to say, okay, if this function returns a particular value like none, then, there was something wrong with the socket, so deal with that, and if you're okay, then keep going on. That's just, it gets gross really fast. You don't have a lot of information coming out unless you get all kinds of extra error codes, and this isn't C, it's Python. We have something called exceptions. So don't bother with if your response comes back normally, then everything's fine. If something's not fine, raise an exception. This way you can also clearly have different classes of failures. So in this case, we might be expecting a connection error here, like a drop connection or something. We'll handle that and move on. Again, it catches the errors right away, and if you don't capture the error, if you're not structuring your code properly and wrapping them and trying excepts, that'll become pretty obvious when an exception bubbles all the way up to your test framework. Whereas if you just didn't check a return code, again, you're sifting through logs trying to figure out where something went wrong. All errors are not the same. There's two kind of classes of errors that I usually like to identify. Different people call them different things. I tend to call them transient or permanent. Transient errors means it's probably something temporary. It may not be, but it might be. So just try it again. So again, this would be like a drop connection. Just because your connection dropped doesn't mean that your device is on fire or anything. It could just be that there was a hiccup in the network, something like that. So you should give it a try again and hide this from the application above. And then permanent errors is, sorry, we did everything we could. That's if your device is actually on fire or something, which doesn't actually happen that often, actual flames, but crashes happen all the time. Another way of slicing up your errors into the error layer cake, as I described it, is kind of, in automation in particular, there tends to be 4 sort of layers of errors, from the lowest level on the top to the highest level on the bottom, which is kind of unintuitive. Sorry, maybe I'll flip that next time. The first 2, data errors and connection errors, these are usually not fatal. They might be in the end, but basically this means data got corrupted somewhere in the transaction, or like I said, a connection dropped. You should probably try to redo this a few times and keep this within the scope of the networking layer, isolated from your higher level applications. Your test that's running running something on, say, the Android Firefox that's trying to tickle something or load some particular page. It doesn't care if your connection dropped and you had to reestablish it. Don't just isolate that away. And most importantly, don't bother with a lot of data integrity checks, like checksums and, hey, did you get these bytes, that I sent you and everything. TCP does that for you. This is assuming you're using TCP, which you probably normally should be. UDP is a different story. But generally speaking, don't waste time doing checksums and everything. TCP already does that. You want to worry about the higher level errors, like connections dropping and things like that. At 2 levels higher than that, the device and at the application. Device errors is a fault of the device itself, like an SD card on a phone going bad, which happens all the time. That's a problem with the device itself. You need to report it up to the higher levels, but there's a different action that you will take if it's a device error versus an application error, like a missing file or something. The application errors means your test failed for good reason. There's a bug in your product under test, or there's a bug in your test framework itself. All these errors have to be addressed, but there's different ways of addressing them, and make sure you call them out into whichever category they're falling into. And they're usually fatal, like I say. Third part of the whirlwind tour of network programming for automation. Design effective protocols. Now, something that, again, seems obvious, but isn't necessarily, is that as automation developers, our primary users of our clients and servers are other machines, not people. We might be using them to test it out and everything, but when you're set up, the whole goal of automation is that it's hands off. So it's easy to forget this while you're designing and implementing your protocol. So for example, you start off writing your protocol. You're going to start with the easy commands first, of course, because you're lazy like me, and you want to put off the hard work. So you want to do a few commands like that get, say, the operating system, or that list files on the SD card or something, right? So this might be what your protocol looks like. You log in to test these things yourself, right? It's really simple. You're just wanting to split. Just use a command prompt because you're kind of you're thinking of it like a shell. So it's really easy to implement. Just output a prompt, and then when the client gets it, it'll just split it by the prompt and then take the pieces out and process them as responses to commands. But wait a minute, now you've gotten to the harder parts of what you have to do, and you're realizing you have to push and pull files back and forth. That involves binary data. Well, if you're looking for prompts to separate everything, you're in trouble, because even if your prompt, say, is 2 characters long, every 64 kilobytes in purely random data, you will come across this prompt. And then you're going to have to try to separate out, wait, is this actually a prompt, or is this just happen to occur in the file that I'm pushing? It's particularly bad if you're, say, pushing logs of your connection back and forth. So then you think, well, okay, I'll just make a special case for this transaction. So this particular, command, the get command, might return the file name and then the number of bytes to expect, like that. But really what you got now is you got a protocol that essentially has 2 modes. You got a prompt separated mode for all of your kind of text terminal-like things, and then you have a byte counted mode for all of your data transference. And you got 2 code paths, and everything gets more complicated. You got to do more testing and everything. Really, in the beginning, you should have designed your protocol for a machine. Humans are good at context. We can look at a blob of binary data and realize that the stuff that comes after the prompt that's hidden in there is probably part of the file. Machines aren't as good about that, about context. They're really good at counting, though. We don't want to count out all the bytes. The machines, why not? So design a robust protocol. You still want to keep it fairly simple for automation, but just for instance, make sure that there's a length parameter for all of your requests and responses. Of course, humans are people too, so you want to actually be able to use your client and server from, say, a command line. Well, rather than just telnetting in like you would normally do to test it, just write a simple command client. There's kind of examples of what we've done here. We have a command client that abstracts away the underlying protocol so that we just launch some commands, like getting the operating system look more or less the same as telnetting directly to the connection, but pulling a file lets the client and server do its magic and hides it from you. So to sum up, learn how sockets work before you actually sit down to start designing your socket protocols. Expect errors in the automation. They're going to happen. And understand there's different classes of errors. And design your protocol ahead of time. And remember that it's going to be used primarily by machines. And a little pitch for what we do. This QR code here will take you to our wiki page for automation and tools. Anybody is ever looking to get some experience in automating things, be it mobile or otherwise, feel free to drop onto our IRC channel or show up or look at our wiki page. Any of these things, we're always looking for contributors. If you want to learn, if you want to help out with our project, we usually have a handful of them at any time. We actually have contributors mentoring other contributors now. So we give nice, gentle introductions. There's a page, I don't have it linked here, called Bugs Ahoy, where you can actually find Python bugs throughout the whole of Mozilla, but specifically in automation, if that's your interest. And I've got a blog here where I'm going to be expanding this talk into a series of blog posts at some time when I get around to it, and that's the address there. Questions? I summed it up that well, eh? Congratulations, you're all experts.